So let's begin with the direction cosine matrices. The direction cosine matrices are passive rotations, and I like to concentrate on that passive rotation because commonly that's what we want to do. We want to change the representation of the vector rather than rotating it. All right, so let's begin with an example. I have a little cart here that can move sideways like this. It can slide, and then I have a pendulum attached to that cart, and that pendulum is essentially a load. And that load, it has a little sensor here. I have drawn the reference frames for the world frame, which is the N frame, as I call it here, and I've drawn the S frame, which is the sensor frame. It's a sensor. This little square is a sensor that I've placed there, and it's a velocity sensor. And what I want to show with this example is that if you want to compute, in this case, the velocity of that load while this cart is moving, and that sensor is only reporting velocities on its own frame, and this little cart only reports velocities along the global frame or the N frame. How do we combine this information so that we can get the velocity at the load, in this case the total velocity at the load? How do we combine these measurements, some that are in the N frame, some that are in the S frame, so that we can get the total velocity? So that's when direction cosine matrices become very useful as a tool to do the operations that we need to do in order to do these summations or to do these operations.